Now let's look at the ratio test. So the ratio test looks at the limit as n goes to infinity of the ratio of two terms in the series, an plus 1 over an. So that's just putting two consecutive terms of the series into a ratio, and then looking at what happens as n goes to infinity. And if the limit comes out to be a value that's less than 1, what that shows you is that the series is absolutely convergent. If the limit comes out to be greater than 1 or is equal to infinity, then that shows us that the series is divergent. And in the case when the limit comes out to be equal to 1, then the ratio test is actually inconclusive, so we might need to consider another test. So we want to, as best we can, try and avoid this third case by looking at the cases when we know that the ratio test is going to give us some conclusive result. So let's try an example. So when I look at a series like this, we got the series -1 to the n cubed over 3 to the n. And if I want to determine the absolute convergence of this test, I can consider the ratio test, and I know that it's going to give me a good conclusive result because it contains this 3 to the n inside the series. So that's a dead giveaway that here, when I do that limit of an plus 1 over an, that it's going to simplify to something nice that's going to actually have a limit that's not equal to 1. Okay, so let's work it out. So we want to work out this limit and see what we get. And in this case, remember that an plus 1 will be putting in n plus 1 into the series, or into the term here. So -1 to the n plus 1, n plus 1 cubed over 3 to the n plus 1. And then we'll have divided by an, so this is exactly how it is. So I could divide by an, or here what I'll just do is I'll multiply by the reciprocal of an. So just flipping it over here. And then let's see how this simplifies. One thing I noticed is that because it's in absolute values, these -1 to the n factors we can ignore. Those will go away because of the absolute value. And then here we can look at 3 to the n divided by 3 to the n plus 1. Think of 3 to the n plus 1 is 3 times 3 to the n. So that'll divide with the 3 to the n up here, leaving me with just a factor of 3 downstairs. So what are we left with now? So I have n plus 1 cubed over n cubed, and then there's also a factor of 3. And I got to make sure that I remember it's in absolute values. But in this case, that wouldn't make too much of a difference because actually here n is going to infinity, so it's given that n is positive. So here the absolute values wouldn't make much of a difference. And now let's take the limit as n goes to infinity. Notice that both of these have a power of 3. And then this 1 over 3 factor I can take out in front. And then I can put all this other stuff, the power of 3, on the outside. Since it's got a constant power here, I can move the limit inside the parentheses. And then whatever the answer is here, I'm going to raise it to the power of 3. And now the nice thing is that this limit here is equal to, well, you can simplify n over n plus 1 over n will just be 1 plus 1 over n. And this will go to 1 plus 0, so it'll be 1. 1 to the power of 3 is just 1, so this is equal to 1/3. And it came out, in this case, to be a value that's less than 1. So remember, that implies that it's absolutely convergent by the ratio test. Let's try another example. In this case, we want to test the convergence of the series n to the n over n factorial. Here's another great example of how the ratio test will be well suited for series that involve factorials. So if I see a series that has factorials, I know that the ratio test will usually give me a conclusive result, so it'll be a good choice. So let's try and work it out. So again, here we're taking the limit as n goes to infinity, and an plus 1 over an. So an plus 1, that'll be n plus 1 to the n plus 1 power over n plus 1 factorial. And then divided by an, I'll just multiply by the reciprocal of an. So we'll multiply by n factorial over n to the n. Now let's see how this simplifies. So actually, one thing I notice is that these factorials are going to simplify very nicely, because n plus 1 factorial, if we think about n factorial, what is n factorial? That's n times n minus 1 times n minus 2 and so on, right? So it's all the numbers that are going from n all the way down to 3 times 2 times 1. So it's just multiplying all the numbers from n down to 1. So what is n plus 1 factorial? Well, that's going to start with n plus 1, and then the next number below n plus 1 will be n, and then n minus 1, n minus 2, and so on. All the way down to 3 times 2 times 1. So what we actually notice here is that starting from n down to 1, that's actually n factorial there. So what we see is that here, n plus 1 factorial is really equal to n plus 1 times n factorial. So with that, we can use that to simplify the n factorial in our limit here. So here this n plus 1 factorial will be n plus 1 times n factorial, and then that will divide with the n factorial we see here. So what are we left with now? Let's write it out. We've got the limit as n goes to infinity, n plus 1 to the n plus 1 power. Here the n factorial divides. And then downstairs here we got n plus 1 times n to the n. Now I notice that one of these n plus 1 factors divide. So let's see what we have now. We've got the limit as n goes to infinity, n plus 1 to the n over n to the n. Since they both have a common power of n, we can put them all into one fraction. This is n plus 1 over n to the n. Notice that it's actually now an indeterminate power. You got something inside the power or in the base that approaches 1, and then something in the power that approaches infinity. So it's an indeterminate form of the type 1 to the power of infinity. So remember, this is the type where we need to use a little bit of manipulation to get it into a form where we can use L'Hopital's rule. So actually here, let me simplify the inside a tiny bit, and maybe you might recognize here if I go n over n is 1 plus 1 over n to the n, you might recognize that this is the limit that gives me e. So let's actually work it out here. I'm going to work it out using L'Hopital's rule. So remember, let me remind you here, if I've got the limit as n goes to infinity of 1 plus 1 over n to the n, right? We said it's in that 1 to the power of infinity form. So we want to be careful here. This is going to be an indeterminate form. So we need to manipulate it a little bit. So I'm going to write this as the limit as n goes to infinity of e to the ln of 1 plus 1 over n times n power. Okay, then I'll flip over the n here to bring it to the denominator. Bring the limit in the power as well. So I've got ln of 1 plus 1 over n divided by 1 over n. So I flipped over the n here to bring it to the denominator. Now it's in the form 0 over 0. As n goes to infinity, ln of 1 plus 1 over n goes to ln of 1, which is 0, and 1 over n goes to 0. So now it's in a form where we can use L'Hopital's rule. And taking the derivative of ln of 1 plus 1 over n, that'll be 1 over 1 plus 1 over n times the derivative of 1 over n, which is negative 1 over n squared. Downstairs we'll have the derivative of 1 over n, again, is negative 1 over n squared. And then dividing those guys out, we're just left with e to the limit as n goes to infinity of 1 over 1 plus 1 over n, which is e, right? E to the power of 1. Notice that we wind up with something here that's greater than 1. And so, keeping in mind that this was all just to get the limit of this ratio, an plus 1 over an, since we get a value here that's greater than 1 by the ratio test, this implies that it's divergent by the ratio test. Okay, so whenever this limit comes out to be something that's greater than 1, we know it's divergent. So here's some quick notes that you might want to keep in mind when dealing with the ratio test. The ratio test works well for cases that involve exponential expressions, such as b to the n, or factorial expressions, right, with n factorial. Because, as we saw in those last two examples, that an plus 1 over an is going to simplify into a form that will give us a conclusive result, in other words, a limit that's not equal to 1. Another thing to keep in mind is that the ratio test does not work well in cases that involve powers of n, such as rational or radical expressions, and these will always be inconclusive with the ratio test. And therefore, you should avoid using it when you see stuff like 1 over square root of n, or n squared minus 5 over n cubed plus 1. Okay, so that's a radical expression, that's a rational expression. So don't use, so if you see a series like that, don't use ratio test. We know it'll always be inconclusive. Okay, And in fact, we know a better method for dealing with these, which is to compare it with a p-series, because here 1 over the square root of n actually is a p-series. Or if it were something maybe a little different, then you would compare it with a p-series. Same here, this is n squared minus 5 over n cubed plus 1. You would compare it with the p-series using the comparison test.